Right. So that's I kind of have a vague plan for my 3 lectures. And the plan is first, today I want to give some definition and consequences. My second lecture I thought would be about SL3R and SL3Z. I could say something like lattices and semi-simple Lie groups, but I'm just going to stick to SL3R. And the third lecture, I wanted to say other stuff. Related. So I have a few plans, and if I really fuck up my 2 lectures, maybe I'll just finish whatever I was planning on saying in the first 2 lectures. Okay, so right. So first, let's start with some motivation.
Would you like to have more space?
So one thing that we all know, and I'm sure that if you don't know it right now, you know it, it's that SL3Z is finitely generated. And it's actually finitely generated. You have some generating sets that are better than others, but one that we commonly use is those elementary matrices. They have ones on the diagonal, and they have a 1 somewhere else, and then they have zeros everywhere else. And if you take an elementary matrix and an n by n elementary matrix, and you multiply any other matrix, I forgot right or left, what you're going to do is add the ith column to the jth column. And if you take a power of your elementary matrix, you're going to put an n here. And so you're just using elementary matrices, you can do your row operations. And then you teach your student that if you do enough of row operation, you're going to end up, if you start with you're going to end up computing the determinant, you're going to end up diagonalizing your matrix. And if the matrix you started with a matrix in SL and Z, once you diagonalize it, you just have plus or minus 1s on the diagonal, and then you get rid of the 1 is 1. And then you have permutation matrices. Really what you're doing is you're finding a path from the identity to your matrix just using those elementary matrices. So not only you know that SLNZ is finitely generated, but you've probably been teaching it to your students too. All right, so that's a case that we all know how to do. And another case which is very interesting is if you have gamma, which is in SLNR, and it's a co-compact lattice. So it's a discrete co-compact subgroup. Then you can also find a finite generating set, and the way you're going to do it, so this is G, kind of schematized. And then I have my lattice sitting co-compactly in here, and you take R large enough so that G is contained in all the balls of radius R centered at element of the group. And that's gamma and gamma. And, right, so you cover your groups with balls that you center at your discrete co-compact subgroup elements. And then you look at the sets of elements in gamma such that when you move your ball, So you pick 0, you pick a base point, well, the identity. In fact, yeah, this works the same if G is not a group, but it's a metric space with a co-compact action. Well then, wait, okay, wait, so such that S x0 R intersects the goal to this R, non-trivially. And in fact, that's going to be a generating set for a group, because if you take any other gamma, which is somewhere here, so here is x0, which is the identity. Now you take gamma x0, you take a path. So what you need so SL and R is fine, but what you need if it's a metric space, you need it to be connected. So you have a path, you have your interval, you have, since your interval is compact, so you have interval path from x0 to gamma x0. It's covered by goals, it's compact, you extract a finite cover, and that finite cover, which I will draw it in blue, will give you a generating set. Well, we'll give you a path from the identity using only those elements. So you cover by intersecting balls. So in fact, S generates. Right. So this is the right. So but the question that was open back then when Kazhdan did his work is, what about the other lattices? And so I'm not going to really, this is really just a motivation. I'm not going to talk about lattices much or at all. You can build them using extensions of number field, and you get a discrete subgroup in SLNR or in some other Lie groups, but it wasn't clear how to prove that those were finitely generated. And that's the question that Kazhdan was answering in his paper when he did property T. And oh yeah, so it just most of what I'm going to tell you today comes from Alain Valès and Pierre Delar's book. But, well, I thought it came from here. In fact, yeah. But in fact, when I prepare my talk, some of it comes from here. Some of it comes from the new book. They have another book, which is much bigger than Fate on My Bag. There's also a book by Margulis, and there was Kazhdan's original paper, which I included here. It's a 3-page paper. How hard can it get? So anyway.
And he was 17 when he wrote it.
And he was 17 when he wrote it. Yeah. So I went back to reading this paper to prepare this lecture. And I was like, trying to analyze every single sentence. Like, maybe I shouldn't spend too much time on every single sentence, because after all, he was a 17-year-old. But anyway, all right. So okay, so I'm going to start with
we don't have to.
G is locally compact. Second countable group, which means that in my head it's discrete, or it's SLNR. And I'm going to be looking at G hat, which is the strongly continuous homomorphism from G to the unitary operator of a Hilbert space. So this is a Hilbert space. And strongly continuous means that if you look at the map that attach from G to pi GC is continuous for all exceeding H. It also means that if you think that all groups are discrete, you don't need to care about that piece. Oh, and I want it to be irreducible. And this sits in another space, which I'm going to call G twiddle. And it's the same one, but they're not, all of them potentially reducible. So you just drop, yeah, not necessarily irreducible. But still, you want the strongly continuous ones. All right. So this is a set for the moment, and we're gonna look at the topology. Well, it's a set. It's not even true. But I'm not going to dwell into that. I'm not even going to write anything about that. If you suppose that your Hilbert spaces are separable, have countable bases, then that's fine. You're in a set. So you should always do that. Okay, so topology on G twiddle and G hat is given by a basis. I'm just going to describe a basis for the topology. It's kind of, if you had a metric space, kind of describing open balls, but it's not a metric space. So just a topology that I gave by nicer pieces, and the nicer pieces are given, I take epsilon greater than 0, I take psi 1 to psi n in H. So I start with, take a point which, I take a unitary representation. So it has a Hilbert space attached to it. It's a homomorphism with a Hilbert space attached. Unitary. Unitary. It's norm 1. Normal. Hilbert spaces have a scalar product, and it's U star U is equal to 1. Your unitary operator. Right.
Have you fixed a Hilbert space, or is G hat ranging over all Hilbert spaces?
Ranging over all Hilbert spaces. This is why if you don't take the separable ones, you have something which is not a set anymore.
And are you considering the representations up to equivalence?
Yeah, I'm considering the representation up to equivalence. So unitary. So it means that the norm of TG psi is the pi g psi is equal to the norm of psi. And right, I am considering them up to equivalence, meaning that I'm going to say that two representations are the same if you can conjugate one into the other using a unitary operator. All right, so topology. Right. Epsilon greater than 0 and vectors in H, and K contained in G compact. and I'm going to tell you who is in this neighborhood of pi h. So pi prime h prime belongs to this epsilon psi 1 to psi n k neighborhood of pi. If right, so it's in this neighborhood if you can find psi 1 to psi n prime in h prime, such that the difference between pi g psi I and pi prime g psi I prime
In the morning,
is
someone just
uh,
flipped it.
less than epsilon.
If that would be possible, that would be great.
Okay, so what does that mean?
Okay, right?
Thank you.
It's an act of rebellion. Okay, so what does that mean?
Thank you.
Really, to be close to
Are the inequalities for all G and K?
no, it's for all G in K. Yes. Yes. So what does that mean? You have your unitary representation. I draw them on the ball because they're preserving the norm 1 vectors. So this pi is going to do stuff to those vectors. So this pi is moving those vectors around. And you're going to say that pi prime is closed if you can get pi prime to do epsilon the same thing on another set of vector in his own representation. So basically you're going to say that, so heuristically, pi prime is close to pi if it can mimic pi on a finite set. Right. Okay. Right. Okay. So that's the topology, and so let's look at what we can find in G and G twiddle. So one thing that's always there is the trivial representation. So the trivial representation goes from G to the unitary operators of C, which is S1, and it's going to take G and map it to 1. To the constant function 1 that does nothing. So that's the trivial representation, and I've always thought that, oh, I haven't given you the definition of property T, so maybe it's a good time. So, definition G has T if T in G hat is an open set. That's one definition. I'll give you more later. And okay, so right. So I've always thought that you say property T with T in parentheses is open in G hat. It's not going to be open in G twiddle, but it's open in G hat. So I've always thought that I've always been told that you say property T with yes.
I'm confused. So T is one representation, right? So
T is one representation.
But so you want that particular point to be open.
That one.
Yeah,
And you don't care about the other one, even though that's not true. You'll have to care about the other one. But that's right. So yeah.
No other representation can mimic.
Exactly.
Okay.
Exactly. So I've always been told that, and I thought because somehow that you say T in parentheses because T is the trivial representation. It has to be isolated because it's open, so it has to be isolated from the rest of your space. But in fact, Kazhdan didn't put the parentheses on it. So I think I think Margulis is the one who put the parentheses. And I don't know if it was a pun intended by Margulis or not. But anyway, okay. So I gave an introduction to property T 20 years ago when I was at Cornell, and the American students somehow hated Hilbert spaces for some reason. So they kept saying T is for terrible. But in fact, no, T is for trivial. T is for trivial. Okay. So basically, okay. So I was on what else can you find on in G hat? So I have the trivial representation. I have the regular representation. So this one I call lambda G to the unitary operator of L2 of G. All right. So if you're a locally compact second countable group, you have something which is called a hard measure, which is a left invariant measure. It's not necessarily bi-invariant, but you have a hard measure, so you can do L2 functions. And if it's a discrete group, then it's your hard measure is the counting measure, so it's little L2. And right, so that's the regular representation. You have it for any group, and what does it do? What does it do? You map G to lambda GG. So it's going to up on L2, so you're going to give it an L2 vector. And you're going to see what it does. And in fact, it just moves your function. An L2 function is like a bump that goes to 0 very fast. Or fast, depending. So C of G inverse X. So it just moves your thing around. And right, so that's one thing that you always find in G hat. And then you also have semi-regular representation. So you take H, which is a closed subgroup. And then now you're going to, again, U of L2 of G mod H. So you have to think about why you get a nice measure of G mod H. And now so it's going to be the same, right? So lambda G mod H G of C. Now X is not an element anymore, it's a coset. So let me just call it XH. And I'm going to do C of G inverse XH. So G is going to move your cosets around. And so when you act on the L2 function, it's going to move your, it's just going to move your bump around. And so if we look at this quasi-regular representation, we can see that this one always has an H invariant vector. Who is the H invariant vector? It's the Dirac mass at the H coset. The vector whose value is 1 on the H coset and 0 elsewhere. If you move it by H, it's not going to move.
So G is discrete in this example.
Oh yeah, my God, G is always discrete. Okay. So G discrete. Then lambda G mod H always has this H invariant vector is not moved by H. Okay. So in general, if you have a nice enough action of G on measure space, then you get a unitary representation, but I'll talk about that later. So for the moment, that's the first thing that are always there in G hat and in G twiddle, and the point is that in fact there is much more. But really much more. Apparently it's a complete jungle. And I don't really know what's in there. But by just knowing this thing about the trivial representation, you can still do stuff. And this is what's so important, is that there is this space which is a big jungle and we don't know how it looks like. But just out of knowing that this one point is open, you can do stuff. And so let's look at what we can do. Until what time do I have? Oh, 2:30. Okay, I'm going way slower than expected. Okay, let's just remove that. Okay, so first we're going to look at what it means to what it means for other representations to be close to the trivial representation. Because the first definition is on the trivial representation in G hat, but then this one's never this. So the trivial representation is irreducible. Oh yeah, I should tell you what irreducible is. Irreducible means that you can't find a smaller piece in it. Meaning that you don't have in H a subspace that's invariant. By the way, I don't know how much you know about property T. I'm slightly intimidated by the fact that I know that some people know more than me in this classroom about property T. So if I leave out if I leave out stuff I shouldn't be leaving out, don't hesitate to ask a question. All right. Okay. Right. So this is something I already said. So pi is equivalent to pi prime. Means that there exists a going from h to h prime unitary, and such that pi prime g is equal to a pi g a inverse for all g, and it's irreducible. Did I already say irreducible? Irreducible. Okay, so reducible. If you can find V strictly contained in H, such that pi GV is contained in V, and then you're going to say that the representation pi V is contained in the representation pi H, and is a sub-representation, right? So P prime is a sub-representation. It means that you can that P prime is equivalent to a sub-representation in pi. So basically, sub-representation, you look at them, and there is a notion of weakly contained, which I'm going to just write here. If you have pi, which is in the closure of a representation for this topology I gave you, then you're going to write like this, weakly contained. Okay, so we had great. So we looked. We said that G has T if this thing is open in G. So what does it mean? What does it mean to be open? So just a remark. If you're an irreducible and if pi has an invariant vector, meaning that there exists psi in H such that pi g psi is equal to psi for all g, what does it mean? It has to be trivial. You can't. Yeah. The only way, if you're irreducible, the only way to have an invariant vector. All right, so let's look at what this definition tells you. So it tells you that if you're So P in pi in a neighborhood of T, so T is my trivial representation. What does it mean that pi is in a neighborhood of T? So since this representation is one-dimensional, the neighborhoods which I have erased, you just have one vector. You take psi, which in C is your only vector, and you take K contained in G compact, and epsilon greater than 0. What you want is that there exists psi in H. So this is pi H. You want it to exist psi in H such that the
Maybe you want to call it psi prime.
I want to call it psi prime. Why?
It's not the same psi.
Oh, that's right. That's right. Yeah. No, I don't want to call it psi prime. Right. So what you want is that ig psi is when you what does a trivial representation do? Is you just want it to be close to epsilon. And then you decide, well, let's write 1 in another way. So it means that if you're in a neighborhood of T, you're not going to do much to your vector psi. And then you have a small remark, which is that if you look at ig psi minus psi, the norm squared, well, that's going to be equal to ig psi minus psi, ig psi minus psi, no. And so when you develop everything, you're going to find twice times 1 minus the real part of ig psi psi. So if that's close to 1, that's going to be close to 0. So so pi close to T means that for epsilon greater than 0, K contained in G, you can find psi in H such that ig psi minus psi squared is less than epsilon. So all my vectors have norm 1 all the time.
So this is again for little g in the compact set.
Yeah, right. For all G compact, in the compact set. So, okay. All right. So, okay. So now that I've given a definition, the next thing is what groups can you find that have property T? So the short answer is that property T groups are not that easy to find. The first ones are easy, and those are compact groups. All right, maybe I'll leave it here. I don't know how I should call it, a lemma or whatever. Maybe not a lemma, but anyway, proposition. We call proposition. Compact groups have T. And how do you do that? Well, you take epsilon small and G is equal to K because it's compact, so you can take the whole group. And you want to show that the whatever neighborhood. How did I call my group? Yeah, eta. No, I think I should call it X. X. K epsilon. You want this thing around T. You want to show that it's reduced to T in G hat. So you take your so what you're going to do, you have your representation, you have your irreducible representation, and you want to create an invariant vector. So once you create an invariant vector, you're going to say, well, it was the trivial one. So you take epsilon small enough so that when you move your vector, you don't go very far, because we said that it was always so okay, you do that, and then you're going to average, and then you're going to take the average, which is the sum. Okay, if it's compact, you have to take the whole average. If it's a finite group, you just sum everything and the fact that you were not the fact that you were kind of close, it means that your average is going to be non-zero. Right, because when you do this average thing, if you're close enough, you have something that's length more than 1/2, so it's going to be non-zero. So that's non-zero if pi g c minus c is small. And this guy is invariant, because I took everything, so if I act on it, I'm going to permute this thing that I averaged, nothing happened. So this is eta. Eta is invariant. I assume that this thing was irreducible, so I have to leave a trivial representation. Okay, so and then what's interesting is that in Kazhdan's paper he writes as if it came as a surprise, and in fact it's not an equivalent relation. It's not equivalent to property T is not equivalent to being compact. But something which he called a bit weaker is that conversely, if G has property T, then G mod GG is compact, and I'm going so much slower that I'm going to do that next time, because that way I can at least prove that the main thing, which is this theorem, which is that I'll get back to that, but this just means that in particular Z doesn't have property T. And right, and so the next theorem is if you have gamma countable discrete with property T, then gamma is finitely generated. So how do you prove that? Okay, so there's so one reformulation, and that's kind of an exercise. You can think about it after. What does it tell you about elements in G twiddle? So T open in G hat is the same as saying that in G twiddle, if you have the trivial representation that's weakly contained in a representation, then it's actually contained. And what does that mean? It means that means that you have almost invariant vectors, and it means that if you have almost invariant vector, you're going to find your invariant vector. And that's the plan was to actually see in Z that you can find almost invariant vectors, and you're never going to find invariant vector because I gave you the regular representation. Regular representation is a place that never has invariant vector unless your group is finite. Because L2, if you want to be invariant, you have to be constant, and you can't be constant unless you're finite. So anyway, let's see if I can do the proof in the -2 minutes that's left. So you enumerate gamma is gamma 1, etc. And then you set...
You have 3 minutes.
I have 3 minutes. Okay, so 5. So I'm going to set gamma n is the subgroup generated by the n first element, and I want n such that gamma is equal to gamma n, and I'm going to look at semi-regular representation gamma mod gamma n from gamma to L2 of gamma mod gamma n. So as soon as you find an invariant vector here, you're done. Because if you find an invariant vector somewhere in one of those representations, it means that this quotient is finite. It means that wait a little longer and you're going to get to gamma. So this has an invariant vector if and only if if and only if gamma mod gamma n is finite, which means that some gamma m is equal to gamma. And so now you take epsilon greater than 0, and you take k compact, which is finite, and then you take n large enough such that k is contained in gamma n, and then you think about it and you see, well, this semi-regular representation now is going to belong to this neighborhood of the trivial representation. Yes?
If gamma mod gamma n is finite, then you already won, right? Because you have a finite index subgroup.
Yeah, right. If it's finite, you win. That's what I need to do. Show that this is finite.
Ah, yeah, sorry.
Yeah, exactly. So yeah, right. So what I'm saying is that you have an invariant vector. It means that this finite. It means that you won. I want an invariant vector. And so I'm going to take f. I'm going to take this thing, and I'm going to say, well, this is in the t neighborhood of x k epsilon. Why is it? Because gamma n has an invariant, because this has an invariant vector, right? So it's in the neighborhood because you can find a vector which is invariant under this whole thing, right? I told you this is eta is delta gamma n, which is the Dirac mass at the identity. It's not going to be moved by gamma n. It's your invariant vector. And right, so that's your almost invariant vector. So you know that you have an invariant vector. And so it means that L2 gamma n has an invariant vector, which means that gamma n is finite, which means that we are done. And so I didn't want to lie totally when I told Alain that I'm going to talk about Margulis results. So let me just mention Margulis results, and I'll prove it the next time. So I've heard the story that basically Margulis was somewhere in Russia and hanging around with people doing real stuff, useful stuff for the society. So somebody told him, like, why don't you do something useful? And he said, I'm going to teach you how you can do electrical networks in an efficient way. And this is what he did. I don't know if it's a myth or not. So basically the theorem of Margulis is that if G has T and take S epsilon Kazhdan here. So S epsilon is the time at which, if you go closer, you have to have the invariant vector. S epsilon is the distance at which the moth is getting burnt on your light bulb, basically. So if you get close to your trivial representation, you have to get an invariant vector. Okay, but there is a point at which you can't get any closer without having an invariant vector. And so that's the Kazhdan pair. And now we know it's finitely generated, so you take a finite generating set. And what the theorem says is that if you take any finite index subgroup in G, then the Cheeger constant of the Cayley graph, which is exactly what Alain defined of G mod H, that the generating set HS is greater than epsilon. Yeah, that's epsilon. Here. So it also means that if you have a group with property T, you can take all the finite quotient in the world that you like. You're going to have this expansion constant that's never getting close to 0, which is false if you start with Z, because as I'll show today, if you take finite quotients of Z with a plus or minus 1 generating set, you get this round thing. And if your quotients are getting larger and larger, your expansion constant is going to 0. It's not going to be bounded away from 0. And I'm sorry it was much slower than expected, but I'm going to stop here. Thank you very much.
Do you have more questions for Indira? So here you're looking at quotients and normal subgroups, because there is also a version of the statement for
there's a
for
no, I'm
triagraphs.
that's a good question. Now that you say it, it could be that the proof I have just works the same.
Yeah, I think so.
Let's see. Well, right. It doesn't need to be normal.
But
Well, you can still define a Schreier-graph if it's not normal. You still have except that I'm terrified by Schreier graphs. I would not.
it's not the same graph.
It's not the same graph. You might want to, I don't know. Yeah.
It might be useful to have those numbers.
It might be useful to, I'm pretty sure you need to, I'm pretty sure you use the fact that you don't have always groups. Yeah.
If there is no more question, I think suggest we thank the speaker again. Now we have a coffee break until 3.